Hi there. Welcome back to Three Inquisitive Kids. Today in Chapter 8, we will be looking at perpendicular lines. Discover the concept and properties of perpendicular lines. This is Part 2 in the positional relationships between lines lesson. Later on, we'll be using the knowledge that we obtained from this lesson and the previous one a lot in the problems. So make sure you pay attention and let's get started. Learning goals. Understand the concepts, properties, and drawing methods of perpendicular lines, and understand the distance from a point to a straight line. Able to apply the properties of perpendicular lines when solving problems. Observe these two following pictures, and can you find any intersecting lines? That's a term we learned in the last video. Intersecting lines are two lines that intersect at one point. And what are their special characteristics? Here we see a fence and a window. Something I see on this window picture is the frame, and we see four straight lines. I'm just going to take this one and this one to show you what I'm talking about. They intersect to make the corner of the window, and it seems to come at a perfect angle. And here we have multiple little rectangles being formed by two long wooden pieces and multiple shorter ones. They also seem to intersect at a perfect angle. But what is a perfect angle precisely? That's what we're going to find out. In daily life, the relationships between two straight lines and a figure are very common. Can you give any other examples? Here we see two roads that intersect at a perfect angle. Also, the corner of a whiteboard or an iPad, for example, would also probably be a rectangle. The properties of perpendicular lines. In this model, if wooden bar A is fixed and wooden bar B is rotated, so they're put together at this point, at this nail right here, but A does not move and B can swing around. When the position of B changes, angle alpha is formed, this angle right here. The new angle alpha changes as the relationship between A and B change. Alpha is a Greek letter. The word alphabet is actually originating from it, alpha and beta, and these are some Greek letters that you might see a lot, especially when talking about angles in math. So that's just something interesting to know unless you're confused. So as B changes, A changes as well. Knowledge checkpoint. The definition of perpendicular. So basically, it's when two lines rotate to make a right angle. When a pair of intersecting lines form a right angle, these lines are perpendicular. And also, when two line segments are perpendicular to each other, it means that their corresponding lines are perpendicular as well. Which means that if, say, we have this line, segment AB, and this line segment, CD, right? They're segments, which means they each have two separate ends. And when I draw it out here, they don't seem that they're perpendicular because they're not touching each other. But remember, the definition of a line segment is that it is a segment of a line, and lines go on forever in both directions. So really, it means that their lines are perpendicular to each other, which means that these two segments are perpendicular as well, even though they do not touch. Okay, so that's something to know. And if you want, you can take out a piece of paper and a pen and you can jot this down. This is very helpful to remember. The representation methods of perpendicular lines. When lines AB and CD are perpendicular, AB we draw this little symbol, which is read as perpendicular to CD, or CD is perpendicular to AB. So this symbol you write in between two line segments or two lines to show that they are perpendicular. L and M represent two straight lines. If L and M are perpendicular, it can be written as L is perpendicular to M, so the same little symbol, or M is perpendicular to L. The point at which two lines intersect to make a right angle, so point O right here in the reference, is called the foot of the perpendicular. The foot of the perpendicular, that is the point where two perpendicular lines intersect. Let's do a problem. As shown in the figure, lines BC and MN intersect at O. AO is perpendicular to BC and angle BOE is equal to angle NOE. If angle EON is equal to 20 degrees, find angle AOM and angle NOC. So I'm just going to add the angles right here. So we know BC and MN intersect at O. Okay. AO and BC intersect, and they're perpendicular. So AO and BC, this would be a straight angle. Notice I'm going back in the problem for reading it a second time to write down its information. Angles BOE and NOE are the same. So I would do this symbol to show that they are the same. And EON is equal to 20 degrees. Find AOM and NOC. AOM and NOC, that would be this right here and this right here. Pause the video and solve the problem on your own. Alright, what answer did you get? Here's the solution. Because, that's the symbol, because angle BOE is equal to angle NOE. Therefore, angle BON is equal to 2 times of angle EON, which is equal to 40 degrees. Which also means that angle ANOC is equal to 180 degrees minus angle BON. NOC right here is the angle we're trying to find. And since BOC is a line, it also means it's a straight angle. Straight angles are 180 degrees. So since we know this portion, which is BON, we can subtract that from NOC to get 140 degrees. Therefore, NOC would be 140 degrees. Angle MOC is equal to angle BON. We know that because MN and BC are straight lines, which means that they are vertical angles. Vertical angles are always congruent. Vertical angles is when two lines intersect, the pairs of opposite angles that they form, they are congruent. Because AO is perpendicular to BC, we know that angle AOC is equal to 90 degrees. AOC is equal to 90 degrees. And we know that angle AOM is equal to angle AOC minus angle MOC. So AOM is equal to MOC subtracted from AOC, which is 90 subtract 40, which is equal to 50. Therefore, angle NOC is equal to 140 degrees and angle AOM is equal to 50 degrees. That is how we get our final answers. What answer did you get? And did you use the same solution? If you use a different one, you can comment that in the description down below, and it'll be very interesting to see how everyone thought of this problem. Activity 1. Can you use a triangular ruler to draw two perpendicular lines on a piece of paper? Now, you may have a triangular ruler next to you, you may not. When we are looking at geometry problems especially, it's really helpful to have a ruler nearby or a calculator in case we have something to do with that in our lesson. If you don't, it's fine. All you have to do is learn the skill. Well, let's take this triangular ruler for example. It's drawn on the screen. This triangular ruler, you will always have a triangular ruler with a 90 degrees. So all you have to do is trace along the edges of that, and then you will have a 90-degree angle. Actually 4, because that's where they intersect. Activity 2. If you only have one straight ruler, so one of those rectangle ones, can you draw 2 perpendicular lines on graph paper? Well, of course, graph paper is already split into tiny little rectangles or little squares. All you have to do is trace on one of the corners of those squares, and then you have a perpendicular line. Since we know that each perpendicular line creates a 90-degree angle, and that all of the interior angles of rectangles and squares are 90 degrees. This is another more interesting way to do it. You could do a cross as well. That also means 90 degrees. Hands-on experiment. Can you fold 2 creases out of paper that are perpendicular to each other? With this piece of paper. Here, you start by folding one crease, then another, and then once you lift them off, you have a perpendicular line. All you have to do is fold the 2 pieces of paper at the same angle and then make sure that they intersect. Now we're going to look at the properties and drawing methods of perpendicular lines. How many perpendicular lines can be drawn for straight line L? How many perpendicular lines can be drawn to straight line L through point A? And how many perpendicular lines can be drawn to line L through a point outside of the line B? Think about these 3 questions on your own. Well, let's imagine for a moment. We have a line L. There is an infinite number of perpendicular lines that can be drawn to it. Any line that forms a 90-degree angle would be fine. You could have a perpendicular line here, 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 and since line L goes on infinitely in both directions forever, there is an infinite amount of perpendicular lines that you can draw. So the answer to this first question would be infinite amount. Infinitely, I'm just going to write infinite. For the second question, there is another property that you must satisfy. How many perpendicular lines can be drawn to straight line L through a point A? A could be any point. All you have to do is find a line that passes through that and intersects with line L to create a 90-degree angle. So here A could be anywhere. It could even be on that line. All you have to do is create a perpendicular line like that. That passes through through point A, and it intersects with line L at a perpendicular angle. Now the third question. So for the second question, that would be only one. Only one perpendicular line can be drawn to a known straight line through a given point. And question 3 is not that different, except that point B cannot be on that line. It has to be outside of the line. So still, just like the previous question, create a perpendicular line, and that is the one and only line that is perpendicular to line L that passes through that one point. As shown in the figure, we're drawing a perpendicular line to given line L. This is line L. First, we line up this ruler, and then using this triangular ruler, we create a 90-degree angle. We can call this point A. And this intersection point, this foot of the perpendicular, O. How many perpendicular lines can be drawn to line L this way? Well, there is an infinite amount of perpendicular lines that can be drawn this way because O can be placed anywhere. As shown, draw a perpendicular line to line L that passes through point A. Well, again, we line this ruler up, and we have to make sure that this aligns with point A. And then we can draw that line right there. We can call this point B, and this foot of the perpendicular A. So how many perpendicular lines can be drawn this way? Only one can, because there is one point A that this line has to cross through and intersect line L at. Finally, we have our third experiment. As shown, draw a perpendicular line to line L through point A, where A is not on the line. So A could be anywhere, and we've chosen to draw it right here. What we do is make sure we align that with the line, put the triangular ruler on it, make sure it's next to A, and then we can draw a line through. Again, the same question. How many lines can you draw to line L this way? Again, there is only one because of that point that you have to cross through. The point fixes the direction that the perpendicular line is coming at, and the definition of the perpendicular line fixes the angle that it's coming in at. According to the previous experiments, what can you conclude? Here's our conclusion. Properties of perpendicular lines. Within a plane, only one perpendicular line can be drawn for a given line that passes through a given point. The point that the perpendicular line passes through can either be on or outside of the given line. So, if I were to draw a perpendicular line to line L through point A can be anywhere, can even be on that line. Now we're going to talk about the distance from a point to a line. As shown, a perpendicular line to L is drawn through point A. Several non-perpendicular lines are also drawn through point A. Here we have these lines. This highlighted in red one, this one is the perpendicular line. It forms a right angle with line L. So we have a couple of questions. Which line segment out of AB, AC, AD, and AE is the shortest? And what can you conclude from this observation in one sentence? Well, AD would be the shortest. Why? Well, first, if you were going to take a ruler and measure all of these line segments, you would probably find that AD is the shortest. But from a more mathematical and abstract point of view, how do you know this? Well, just like from one point to a point, 2 points determine a line, we know that the distance between 2 points, the shortest distance to get from one point to another would be the straight line segment that runs through both of them. Here you can think of B, C, D, and E as separate points. You're trying to get think of B, C, D, E, and there's 4 kids on each of those points, and they all want to get to the candy shop that is at point A, and they're all running in this direction. Who would get through the fastest if they all ran at the same speed and they started at the same time? The kid that starts at point D would get there the fastest and the soonest because he's going in a straight line. He wouldn't have to waste extra time going right or going left. Therefore, the observation is that Among all the line segments that are formed by connecting a point on a given line to a given point A, the perpendicular line segment is always the shortest. Simply put, perpendicular lines have the shortest distance. The length of line segment AD is called the distance from the line L to point A. So if I were to say, what is the distance out of all of these line segments from point A to line L, you would say line segment AD. AD, because it is a perpendicular line, would mean it is the distance. This distance is always the shortest way to get from one point to a line. Class summary. Today we learned about the definition of perpendicular lines. When two intersecting lines create a right angle, these two intersecting lines are called perpendicular lines. The point at which they intersect is called the foot of the perpendicular. We also looked at the drawing methods of perpendicular lines, as well as their properties. We learned two main ones. There is only one possible line segment that is perpendicular to a given line while passing through a given point, and that perpendicular line segments have the shortest distance between a point and the line. Again, that runs into our fourth point, which is the distance between a point to a line. We learned that the distance between a point to a line is the shortest line segment, which is the perpendicular line segment. Again, today we understood the concepts, properties, and drawing methods of perpendicular lines and understood the distance from a point to a straight line. We were also able to apply the properties of perpendicular lines when solving problems. Thank you so much for watching through Inquisitive Kids. If you found this video helpful or if you enjoyed it, please be sure to subscribe for more. Again, we really appreciate your support, and we'll see you next time.